Everybody here is in the class. So.
Required to graduate.
Interest.
Interest. Okay, it's good. Yeah. Yeah. You know, the student in East Coast, can I expect this type of like environment? I mean, it's kind of blessing. Yeah. It's good, very nice. Okay. So
John, do you want to share? This is live. Do you want to share it? Are we like multi-broadcasting?
Yeah, we're multi-broadcasting. This will go into the course as part of the Zoom. I mean, as part of the campus. We'll put a link to yours as well.
So is there a freshman?
No, operating systems is a
Oh,
upper
okay,
level,
still-
so
Oh, okay.
everybody's
Operating
junior,
system.
senior here,
Sophomore.
sophomore.
Some more. Cool.
Yeah.
Wow. Let me see.
Got about 2 minutes here.
So, how many project or programming assignment do you expect more until the end of the semester?
Wait, what, sorry, what did you say?
I mean, how many more assignment do you expect?
A couple.
Couple more?
Yeah.
Okay.
I know we've got some more reading assignments to do for a bunch of different classes. I think as far as we have two longer projects, I have two longer projects going on for both of my classes.
Okay.
So.
They'll be working on a Raspberry Pi
Oh.
implementation of something.
Wow.
There's 4 different projects going simultaneously here.
Mm-hmm. It's good.
Well, I think that's time. I think you could go ahead and start.
Yeah. Okay, so yeah, if you have any questions, yeah, please stop me and interrupt me. Ask any question, okay? So any questions, so basic questions will be fine. So any questions. So I'll be trying to make it easy as possible, but if you're still not sure, let me know, okay? Okay. Have you ever hacked any computer system for fun? No?
I don't think so.
Because it's crime? Oh yeah. It's it's dangerous, right? To do
The most
by
they've
yourself.
done,
Huh?
the most they've done is like looked up when someone has their username and password saved and like change the HTML so you can like see what it is. That's like it.
Yeah. Like using the dictionary of text, right?
Yeah, I guess.
Using
So.
the brute force.
Well, no, I mean literally just changing the HTML from like
Just
password
manually.
string, and so you can
Manually,
see what it is.
right? Yeah, so I mean you can try SQL injections, which is very simple. You can use many different tools, so it's out there, it's open source, but within the closed networks, not other websites. If you do that, probably one day harassment would be. So it's interesting. Today, I'm gonna introduce. Yes.
I'm gonna get a voice box for you.
Oh, it's okay. It's okay. Yeah. Can you hear me backside? Yeah, okay.
When there's outside noise, it's kind of hard to hear, but when it's quiet,
Yeah, I will try to make it louder. Okay. It's fine, yeah. So today I'm gonna introduce some very basic techniques to hack the containers, but it's not exactly in detail. But I'm gonna introduce about like containers, concept of container, Microservice, like that. So yeah, so I'm gonna focus. I'm gonna start from the container security after explaining about the container, concept of the container, and then a little bit about the introduction of the kernel level rootkit, exploring containers, and then general directions, research direction to protect that system from the such introduced threat. Okay, containers. Okay, have you ever used virtual machines? Okay, VMware. Okay, virtual box. Yeah, it's good, right? So you can use the Linux machines in your window, right? Or using the fusions, you can use a window from your Mac computers, right? So those are based on hypervisors, different types of hypervisors technologies. But have you? Okay, so this is a VMs that we normally call. So these virtual machines require guest operating system, right? But have you ever experienced when you run multiple VM machines in your computers? Were you able to easily do other jobs? because this guest operating system is very heavy, right? So have you run the Docker containers before? Okay, it's good. So what is the containers? Containers is the self-contained package, okay, that contains everything that required to run the application, such as libraries and then some other API libraries and then some other database, even the configurations, everything you can wrap into the one files, which is an image, right? So these containers is a technologies based on the operating system virtualizations. What is the virtualization? The role of the operating system is mediating between application and hardware, right? So these OS-based virtualizations use kernel features to separate operating system resources, such as CPU, RAM, and devices. Okay? So this absence of the operating system makes the system more lightweight. Okay? That's why many cloud computing providers or service users use container-based system. So Google's launch 2 billion containers for every week for their internal and external services. Netflix, Visa, all their systems are based on the containers. No, they are not using traditional VM-based. Okay, sometimes they use VMs because of the security purpose. Okay, but most of the internal services are based on purely based on the containers. Okay, so the reason why they use virtual machines and then run the containers on top of the virtual machines, because VMs provides additional layers. Okay, not prevent attackers malicious parties attack. Okay, let's see more in detail. Okay. Compared to virtual machines, the containers takes very little time to start and stop and deploy. Normally, it takes 30 to 40 seconds to start. I mean, 5 to 10 seconds to start, because normally the size of the image is over 1 gigabyte. How about containers? I worked with the undergrad last summer. He said he was able to run over 80 containers in his computers with 2.7 kH, and then two core computers with 8 gigabytes of the RAM. So it was very fast, right? To start, and to deploy. That's why it's easy to migrate for cloud computing services. That's why adopted by many different service providers. Okay. What about the security? Okay, let's just see about the security. So containers provide namespace, which is one of kernel features. Okay, what is a namespace? Namespace is isolations. Whenever the container is created, okay, each namespace, which consists of 6 namespaces, is given, which is mount, which is a file system, PID process ID, network stack, and the inter-process communication, UTS, and user IDs, domain names for UTS. That means, so you have one computer, and when you run multiple containers, the users running one container cannot access file system running in different containers. This process, one process running in container A cannot access processes running in different containers because of the namespace features. Okay. So that's why namespace is very important features in terms of cybersecurity, okay, between the containers. Okay. But what if there is vulnerabilities in kernels, okay, and then attackers exploit such features to make malicious containers can access processes running in different containers. If those containers are being used for external services by the Googles, Netflix, or Pizzas, it's going to be disaster, right? That's why security is really important in this case. So, okay, so I'm gonna show you how to exploit. Okay, such. I'm gonna show you first vulnerabilities, how to exploit it. Okay, before that, what is the kernel? Because kernel features is a key in these containers for security. What is the kernels? Generally, kernels is a core part of the operating system, right? That is responsible for process management, memory management, networks, okay, and managing devices, right? So between hardware and then application, there is OS. OS is composed of kernel, shares, utilities, right? So kernel is a core part. Okay. And then, what is the system core? System core is an interface between user mode and the kernel mode, right? So whenever you execute some programs, okay, these programs, okay, this is one of the examples. Okay, there it is divided by user mode and kernel mode. Okay, you can divide it into two modes, right? So when you execute program applications, normally these programs, for example, these applications execute VE, which is one of system call. Okay, this execute VE is a system call to run the program specified in the path. Okay? So what it does is these applications runs system called refer functions, okay, with the same name, residing in the user mode. Okay? And then these refer functions interrupt, create trap, okay, trap. So using the interrupt instructions. Okay? From these executions, user mode and kernel mode is changed. Okay? So from here, trap handlers takes care of call from the refer functions. What it does is that check the system call tables. Okay? So because execute V has the system call number 11, okay? There is a tables. 11 has the mappings, okay, which is address the real system call routines, which is execute V. Normally it is called sys execute V. Okay? The system call has the mapping information, system call numbers, and then system call routines address. Okay, address of the system call routines. Okay? So, because containers use the kernel features, which is a namespace, attackers all the time tries to exploit the kernels. How do you do that? Using some malwares, which we call kernel level rootkit. Okay. So most popular techniques of the used by the kernel level rootkit is the hooking. Okay, hooking means 90% of the attacks by the kernel level rootkits by hooking. What is the hooking? Hooking is is changing the execution stream, execution flow from A to B to A malicious containers, malicious logic, and then functions again. Okay. Changing the execution stream, okay, and then finally restore back to B, okay, to hide its activities. Okay. So suppose that function A is the trap handler. Okay. This is the trap handlers, and then system call, sys execute B, something like that. So when the target containers calls function A and then B, kernel level rootkit is loaded into the kernel memory, and then change the system call tables by replacing the execute B's address to the malicious modules address. Normally, this modules is separated from the kernel level rootkit. It may be loaded as a kernel loadable kernel modules, okay, which we call LKM, loadable kernel. When you patch, okay, patch device drivers into your Linux machines or Windows, okay, so such loaded modules is going to be pushed to the kernel level, kernel mode memories, kernel memories. Okay, this is the actual code. So this is the LKM, loadable kernel modules in the Linux. When the modules is loaded into the kernel memory, what it executes is this. Okay. For example, in case of mkdir, one of system calls, the address of these hookings, malwares, the address is going to be registered to the real sys mkdir. Okay. And then it executes these routines. Okay. Here's what it does, it just print out. Okay. With path name and then the user mode with the root permissions. And then after doing its job, the return real mkdir to hide, okay, to make it real. Okay. And then once it is done, when the module is unloaded, the original system calls routine is restored back to. This is general approach. Okay, if you have any questions, yeah, I mean, yeah.
So, where is this, the printout of what it's doing, where is that going?
Okay, this is just instead of this printing out, so attackers insert malicious logic in there.
Yeah. But where is that going right now? Is it going to the kernel log?
Yes, kernel log.
Okay.
Yeah. So, ins mode, and then you can check the log information.
And then this is a standard kernel module process, right? So like
Yeah.
the fact that it's, whether it's a malicious module or it's not a malicious module, this same business happens with
Yeah.
the blue, right?
Yeah, exactly.
And so the threat is if you load a module that's malware and you don't know it.
Yeah. Any other questions or? Okay, let's continue. So from now on, I'm gonna show you. I'm going to introduce 4 different scenarios. Okay, using namespace. First, mount namespace break. Okay, so what is the mount namespace? As I mentioned before, the containers running in the one host cannot access files. Okay, cannot read, write, okay, to the files existing in other containers. Okay, so even though you write something in your file system, others running the other containers cannot access it. Okay, but here's what we did is we were able to see the key loggings through the VFS swapping. So VFS swapping is VFS is a virtual file system. Okay, so your kernel is running, but you can have different types of file system. So VFS is running, sitting between the kernels in different types of file systems. So VFS provides interface so that your kernels can run in any types of file system. So what we did is to, okay, before that, also there is a kernel structure which we call task_struct. This task_struct is a large structure with pointers, okay, pointers to process related informations, okay, including file system. And then, yeah.
Our class would know that as the process control block,
Okay.
probably.
Okay. So I'm gonna skip. Also, FS struct contains the file system related information such as UMask, right? UMask, when you create the files, UMask provides a default file permission, right? RWX, RW, something like that, right? So, and then provides root directories and working country, present working directory information. So these task structures point out to the file structures. So that is the mount namespace. Okay, and then this rootkit calls malicious container to log keystroke pressed in target containers. So what we did is to by hooking the sysread. Whenever the users type some letters, okay, from your computer, like a keyboard, okay, this sysread is called, okay, and then this sysread is hooked, and then finally execute the root read. Okay. This root read changes the file system of the process to be the file system of the malicious containers. and then write to the files. For example, here. Okay. So this is a system call table sysread. Okay. This function handlers whenever target containers like enter some keyboard keystroke calls from that activity, syscall is read. Sysread is called executed. By this kernel level rootkit, it changes the execution direction from here to here. Okay, and then what it does is change the task structures of file system structures to be the target containers file system structures. As a result, before change, so C1, which is normal containers, made some files like using echo. Okay, secret information is under test file. Okay. After that, when you try in different containers to see the home test file, but you're not able to see it. Okay. But after changing it, after changing the C2's task structure to be the C1's file system structures, you can see the messages written to these test files. After writing it, it stores the process's original file system and returns the original sysread. Second attack scenario is using breaking the PID namespace. Okay. Normally the container is running on the host, right? So what happens when these containers create one process, okay? Between this container and host, there is a PID namespace hierarchy. In this hierarchy, whenever you create a process in the containers, these processes actually has the different names in upper layers, PID namespaces. Okay, this is a OS kernel features. Okay, that's why host can see the files in the processes in container 1. Okay, because of this PID namespace. Okay. Actually, this process, okay, is running in host, right? But even though this container, the process is running in here, is a root, like a PID number 1, for example. But it is not actually one in host. It has a different names, global names. Okay. Keeping in mind that what it does is to injecting the PID namespace. Like here. Between PID namespace for host and the PID namespace for container 1, we injected PID namespace for the malicious containers. That's why this malicious container names, PID namespace becomes the parent of these target containers. As a result, this process can access this process. So how did we do that? So how do you do the encode levels? So this is the kernel functions. Whenever this function creates the PID namespace, it receives the parent task PID namespace as your argument. Okay. So the kernel level rootkit sitting in the kernels and then change its argument to the malicious containers PID namespace like this. Okay. As a result, the PID namespace, this is a hierarchy, okay? Host, parent, and son. And this is also parent of this target container. That's why this process was able to access all the processes created in these target containers. Okay, the third attack scenario is using the network namespace. Network namespace. So in containers, okay, when you send your email through the Westmont server to external servers, so there is a gateway. Okay? There is a gateway servers, right? So this all the packets go through the gateway servers. Okay. In containers, whenever you create containers, there is a gateway Ethernet servers, which is a Docker 0, which is a virtual Ethernet interface. Okay. In second level of the OSS 7 layers. So when these containers send some packet, okay, this packet coming first arrives at the virtual Ethernet card, which is it's a ETH0. Okay? ETH0 is a virtual Ethernet interface. This packet goes to the Docker 0 and then goes outside. What we did is to insert. What we did is to replace these Docker 0's IP address with a target, with a malicious containers virtual Ethernet address. As a result, what will happen? Every packet coming from normal containers will go through these malicious containers. Okay, and then forward to the real Docker 0. Okay, and then nobody will know. So that's the possible way. So what we did is using these functions. So pip table insert. This is a kernel functions. Whenever they make a route into the routing table, this function is called. Okay, these functions requires pip config and fcgw. This is a argument used by pip table insert. Okay, and then this fc gateway includes gateway IP address as a member. Okay, so kernel level rootkit hooked this function, and instead of executing this, execute this root pip table insert, and then check this fc gateway IP address. If it is the same as Docker 0, it replace with the IP either ETH0 IP address of the malicious container. Okay, next attack scenario is using the namespace, network namespace again. So this is a general. We also exploit the NS proxy. NS proxy is the data structures. It's one of data members of the task structure that I mentioned before. Okay. So this NS proxy contains namespace information. The network namespace NS is one of them. Okay. So these target containers, okay, is working to the with the network namespace pointed by this NS proxy structure. Okay. So what we did is that whenever these malicious containers calls execute B, as I mentioned before, instead of executing execute B, root execute B is called. What it does is to change network namespace of the malicious containers to be network namespace of the target containers as proxy. Okay. Like that. It's very simple, right? So changing malicious namespace proxy, network namespace element to be the target network namespace. Okay. Once it is done, we were able to see all the packets coming through the malicious containers and then forward back to the Docker geo. Okay. So, I mean, it looks very easy, but actually finding out this mechanism was very hard that time. So, any questions so far? Okay, so this is the, this is all the, there are so many different behaviors like that, but this is a representative works that is possible by the kernel level rootkit. Okay. Then how can it prevent? So what's going to be the possible future directions to prevent such problems, or such attacks? That's the human immune system. So yeah, if you have any questions, yeah. So human bodies, think about your bodies. Our bodies is wonderful, right? Why is that? Our human bodies is intelligent, okay, to be adaptive by learning, okay, from the previous experience, right? So human immune system has four characteristics like that. Our human bodies, when your bodies is attacked by the external malicious pathogens such as virus, okay, bacteria, okay, and then parasite and toxins, okay. So randomly checking your bodies, okay, so see what's going on, and then by your immune cells, okay. And then if the body knows about the past histories, okay, by the B cells, they have antibodies, okay, right away detected and cure automatically. Right? Also, if the number of T cells, B cells are not enough, they scale, like a scale out, okay, like make itself by itself. So that's why it's going to be automatically suppress external pathogens. So our body is composed of lymph nodes and lymph vessels. These all nodes filters, okay, working as filters for foreign particles, cancer cells, and these T cells, B cells from the bone marrows, they produce antibodies, and then by collaborating with the B cell, they first check that cell that they found is really good or not. Okay. Body cells, if it is body cell, your cell, you should not kill, right? It's going to be a problem. So first they check if it is my body cells or not. Okay. So that's the adaptive immune system, communicating with the B cells. Yeah, keep in mind that what will be the conventional security system currently we are using? So it can be divided into two parts, okay? Network side, the host side. Right? So mostly the computers that you're using, the host requires antivirus, right? But not many people use the host intrusion detection for firewalls embedded by the operating system. Right? In the level of networks, also similar security tools are required. So in this case, in this environment, we just locate security tools, these tools, in fixed locations. Right? So they are all fixed. And then suppose that there are n processes or n packets coming from the external. And then whenever they process are checked with these tools, they use security policies, right? Policies or rules or signatures, right? So suppose it's n. In a given time, session durations. So overall, the time complexity will be n multiplied by ms divided by l. But nowadays, containers very lightweight, okay? And then people started to think about microservices. Have you heard about the microservices? Okay. Compared to monolithic, right? Monolithic is a big chunk of applications, right? Running as a one standalone application, like that. So if you like to scale out this part, okay, for certain case, when traffic goes very high, you need to scale out this part. Okay. In such case, if you like to scale out this, you need to scale all the part, big chunk of servers at the same time. Even though those two logics are not required, right? If you divide this logic, big chunk of logic into small, okay, and then if you need to scale out this part, you can just scale out this part only, more efficient, right? That's the concept of microservices. So containers very fit to these microservices architectures. Okay, so many developers in the industries, okay, DevOps, have you heard of DevOps, right? Developers, okay, also operators. They are very small number of, like very flexible and dynamic teams. They develop microservice-based architectures and they apply through the containers. Billions of the containers. So if there is a problem, we need some more smart, intelligent approach. Right? So yeah, that's what I thought. About this, like suppose that all these units are microservices. Okay? So microservice is very lightweight, based on the containers. Okay? Like a cells in our bodies. Okay? Cells can be created right away. Likewise, microservices, containers based microservices can be run very quickly, right? Can be very quickly deployed, start to stop. What if we have some bone marrow type of microservices like this? And then we also have a limp microservices. And then this is a general normal microservices, something like a normal cells in our body. And then we train these B microservices and T microservices in the bone marrows using the knowledge. Okay, this knowledge is going to be the, for example, DDoS attack, distributed denial of service attack, has like a specific types, behaviors. Okay, we're just gonna train only for that part, which is K1, and then duplicate some B microservices and then spread into the system. Okay, and then these microservices moving around like our cell. Okay, and then all the packets coming from internal or external collected here and then checks over here. And then T microservices, something like trained from the kernel level rootkit. Okay, kernel level rootkit has a specific behaviors, and then apply in the host, okay, randomly, and then automatically. Once it is detected, automatically suppressed. Okay. So that's why goal is to make this complexity to the S. Okay, everything is parallel by making more scalable, because these microservice container are itself scalable. Okay, this is going to be our general architectures, like yeah. Okay, but what do we need in terms of host and network to train the knowledge? Okay, let's see the first host side. Okay, normally people say that microservices vulnerabilities can be summarized into 4 container issues that we covered first time, and data liquids problems, and the privilege escalation. Okay, privileges running as a normal becomes powerful like a root containers, okay, and the network issues, okay, between the containers. So in a monolithic architectures, the communication between the processes are internal. We only needed inter-process communication. But because we divide into specific logic into the containers, communication between 2 processes becomes external, right? Okay, so that's we call inter-process, inter-service communication. So, okay, so there are 4 different problems, vulnerabilities. Okay, we will be covered about the container issues from here, caused by kernel level rootkit. Okay. We saw like a kernel exploit, okay, also malicious processes, also escaping from containers. So if you are able to see what's going on in the host side, not isolated by the container, it's going to be also a problem. Also poisoned images, networking sharings, all possible vulnerabilities. So these problems caused by kernel rootkit has some specific features. Some are summarized like injections. Okay, we saw like a namespace injection, file activities. Okay, bypass memory write propagation. Normally, the kernel memories are read only. Okay? You cannot write it. Okay? So to protect read only kernel memories, they put CR0 special register. This enabled, okay, to protect. So before patching the malicious memory into the kernel memory space, they first change this bit, CR0. Okay? This is one of possible features. Also, malicious programs track the processes, and we saw they owned their network stack, right? Also, they also modified read-only registers. Also modified the kernel object system calls, right? Trap handler descriptor tables. So all these are possible features. Yeah.
So someone watching online had a question,
Yes.
and
okay.
they asked if you're randomly checking for problems, is it possible that you would miss malicious actors because you're just randomly checking?
Yeah, it's a good question, smart question. So. I'm in the middle of like checking that possibility, so we need like a statistics based on the number of malicious or compromised servers. How many detectors we need? Okay, all should be based on statistics. So yeah, it may be possible to lose such like malicious activities. It's also possible. But it's kind of it's all matter of probability, something like a human system. Our human bodies can miss. So, but we increase the number of T cells, B cells. The person is a healthy man, right? Healthy person. If they are not healthy, the number becomes very small. It's going to be the same. So based on the statistics, we should be able to increase the number of detectors to cover possible problems. Okay, next. Okay, what about the knowledge about the network? Okay. So we have, okay, this internal service communication domain is new. Okay, we don't have much data. But how about this? External communication domains, a lot. Okay, so a lot of data out there. So what we can do is to train from this domain and then apply in this domain using the domain adaptation techniques. Okay. There are some research going on how to adapt domains because there's not many data, okay, and not many labeled data is here, okay, but many labeled data here. We can try from here and then apply to this. So okay, that's the possible way. And then once we train two types of knowledge from the for the BMS and TMS, our human bodies checks between a T microservice, B microservice, which we call handshake mechanisms. Okay, to find out, found a cell is really our body or not. Okay. So if the data between the packet, okay, and the malwares processes are originated from the same attack, okay, and then confirmed by this double handshake, they update knowledge in the BMS. Okay, they are originated from same attack, so you need to update this K data for BMS for TMS. So our system should be able to update in real time, okay, by training. And then if we found the new data, train that new data with the old data again, and then check the validation accuracy. If it's within the threshold, we update new models and then apply again. Something like our human bodies. Okay, this is the yeah. As I mentioned, this is the training BMS. We train inter-service, external, and then going back to model to update the knowledge. Okay, that's pretty much the direction. Do you have any questions? Yes.
So I think all of the attack vectors that you talked about, the 4 different attack vectors, they were all happening at the level of kernel escalation, right? They were the hooking mechanism that you had, where the functions were capturing a method call, doing their own behavior, and then forwarding it to the proper method call. Except maybe the network one. I'm not sure the network one. Am I correct that in order to try and monitor and do the kind of machine learning threat detection that you're talking about, you kind of have to have your software there too, right? Like you have to be writing these kernel modules kind of acting like a hooking mechanism, because you have to see whether anyone hooked before you or hooked after you. Is that the place where you would intervene?
What we can do is to monitoring the, for example, in case of like a system call hookings, system call is not supposed to be written, not supposed to be modified. So there are some research who are looking at the read-only memories, okay, and it checks only that part. If it changes, it's kind of suspect, okay, something like that. So, but that is based on the VMs using the hypervisors. But in our case, containers running on the real kernels. So, like the rootkit, we should be able to have some mechanism to check such areas. Okay. But here also we can bring a question. Then what if such mechanism is put by the rootkit? That's also possible, right? Question. So that's a kind of like a what is first, like a chicken or an egg? Right? We know the answers. Right? So yeah, that's also possible, like a way to think about as a future research.
I mean, it wouldn't be a problem to do that because you would be trusted. Like, presumably the container, people running the container would load your module understanding that you're part of a protection mechanism.
Mm-hmm.
So it's not that you would have to do it maliciously, you just have to use the same mechanism.
Yeah, but in our human bodies also it happens in similar ways. External, like AIDS, like first attack our immune cells first, so something like that. There will be there's also like no malicious kernel level rootkit who attacks the kernel level like detectors first. So yeah, that's why it's very hard to cover the AIDS or like that. So based on the like research, I can actually apply their mechanism in our research. Yeah.
So are there 3 separate models, or is there just one model?
Here.
Yeah.
This graph, these pictures. Yeah, this is just the saying about the knowledge transfer between training microservices and then detectors, which is a TMS, BMS. Okay. Once they found some problems, they update the knowledge here. Updating. That's what it means. Yeah, so.
I got one more
Yeah,
question.
yeah, sure.
Do you want to go?
Yeah, so the action that these T cells and B cells would take would be like notification, killing the process, or how, what, not just the training back to the database, what?
Yes, once it is found that it's really a malicious servers, malicious microservices through the double handshake mechanisms, possible approach will be like suppress, like stop the process, or like block the packets as like traditional ways, and then update knowledge. Or because it's automatic suppressions, possible way also would be like automatic patching. Because the memory is already compromised, we need to patch the memories automatically without stopping the current microservices, which is already going on in UCSB in the security groups. Okay.
I was just going to ask about, like, there's like a spectrum of what's a microservice, and maybe there's something called a nanoservice as well. But what's like, as an example of a microservice, like a database running by itself, and then a web server running by itself, and then like an asset server running by itself, or a microservice is sliced smaller than that?
Yes, normally the network is composed of web servers, web application servers, database servers. These intermediate web application servers contains many business logics in it. So we can divide these web application servers into many. So each individual microservices is connected to part of the databases, partitions of not whole part of the databases, and then later it is updated in the original databases. So basic principle is there only one logic in each microservice. Any other questions? Okay, so briefly, my research. Okay, besides this research, I'm currently doing project with the University, Urban University of Colorado, about implementing deep learning analytics engines. Okay. So these analytics engines provides analytics service to the farmers, okay, who are interested in soil moisture. Soil moisture is very important factor to farmers. So using some IoT user input, such as biophysics data, which is static data and dynamic data like the soil types, moistures and locations. And then with the soil moisture observation data, forecasting data, they train in the system. And then validate, deploy, and then if individual farmers provides individual information from all of the US, these deep learning analytics engines update again and again, and it provides customized information. So supported by the software-defined storages. Okay, this is for 3-year project, and then later, what I like to do is to propose some project to the SASE programs, secure and trustworthy computing programs with these topics. Also, last year I submitted like NSF SIT program signals in the that's signals in the soils. Okay, continuation with the present current project. Also like to submit REU program so that undergrad students can embark the project. Okay, I think teaching plans. Yeah, so that's it. Okay, any other questions? 2 minutes. Any other questions or objections, complaint or anything? It's fine. Yeah. So, if there is a chance, yeah. Yeah. Question? Yeah.
Oh, yeah.
Yeah.
I just had a question
Sure.
about, you talked about you continuously train the model and
Yeah.
then deploy it kind of as it's training.
Yeah.
Like, is that done automatically, or is there like a human like oversight that checks the model's if it's valid or not? Like,
Yeah, it should be automatic. Yeah. So based on the, even though we added new data, if the accuracy is lower than expected, we don't need to update. So based on the validation accuracy, we're gonna decide, okay, to update or not. Once it is done, knowledge also spread to all the systems, the microservices. It should be automatic. Any other questions? Okay, great. And then, okay, thank you very much for listening my talk. If you have any questions, yeah, send me an email and let me know. Okay, thank you. Bye.